In the previous two videos we've looked at Kepler's first and second laws. We're now going to have a look at Kepler's third law, and this one is known as the law of periods. Particularly interesting one, I think, given that Kepler actually developed this purely from observation, and then Newton came along and did something fairly significant with it that we'll get to as we go through this video. And you can see that third dot point kind of gives you a bit of a hint as to what that is. Now, the wording for this one is that the square of the sidereal periods. Now, that word sidereal has a particular meaning. Basically, if you consider with respect to the distant stars. So if you look at the motion of the planets around the Sun and measure that motion based on the distant stars, that would be the sidereal period. Think of it in more simple terms as just being the period of the planet as it makes one full and complete orbit around the Sun. So it's not necessarily for it to complete 1 year. So Earth's sidereal period is not 365 days. It's just a little bit longer than that. So we'll talk a little bit more about that as we go through and look at one of these examples. But ultimately, the square of the sidereal periods of the planets are directly proportional to the cubes of their mean distance from the Sun. Now, when we're talking mean distance, we're basically sort of treating the orbit as though it's circular. So we've identified already from Kepler's first law that they're actually elliptical orbits, but in this particular law, we're basically treating them as though they're close enough to being circular, or if you want to measure the radius at all those different points around as it orbits around the Sun, and then take the average of that. So that's the statement for Kepler's third law. We'll have a look at it in a little bit more of an understandable way by considering the equation that it allows us to develop. So we're going to have capital T here as being the sidereal period, and R as being the mean distance from the Sun. So that means that for any planet, we have the relationship that T squared is going to be equal to some constant multiplied by R cubed. So that's just the relationship as stated by Kepler's third law. So T squared is proportional to R cubed, so in other words, T squared is equal to some constant multiplied by R cubed. The more common way of seeing that being expressed would be that T squared on R cubed is equal to a constant. So what is that value of K? What is it? How do we figure out what that value of K is? I mean, we don't want to have to sit down and make measurements of all of the planets as they move across the night sky and do that for a number of years as astronomers did back in Kepler's day, and use all of that data to then figure out what this relationship is. We can actually now sort of effectively just reverse engineer Newton's law of gravitation. So Newton's law of gravitation is actually just a reimagining, I suppose, of Kepler's third law. So we're kind of undoing what Newton did in order to make sense of this relationship T squared on R cubed. Now, this is something that you need to be able to make sense of. It's not something that you necessarily need to be able to reproduce yourselves, though. So first of all, if we start out with that relationship that we've seen a few times already, so F is equal to G mm on R squared, we've already identified in a previous video that gravitational force is providing centripetal force. So that is another substitution that we can make here. And so if you recall the equation for centripetal force being mv squared on r, we can therefore say that G capital M lowercase m on r squared is equal to mv squared on r. Now, in that a couple of videos ago, I went through and we figured out what the velocity was. We can do a similar sort of thing here again. So cancel both m's, cancel the r on the right hand side and the squared on the left, and we end up with gm on r is equal to v squared. Now though, I don't want to solve for v, I want to use a different relationship here, because you can see we haven't really got t in there anywhere yet. We've got 1r, but we need it to be r cubed. So we know that orbital speed is given by the equation v equals 2 pi r on t. So we can substitute that in for v here. So gm on r is then going to be equal to 2 pi r on t all squared. So a little bit of algebra here. We've got the squared outside, so let's just take that through everything inside the bracket. So that gives us 4 pi squared r squared on t squared. Notice we've now introduced this term of t squared, so that's helpful. And we've got r squared on the right hand side, r on the left hand side in the denominator. So if we go through the algebraic steps here, we're going to multiply t squared up onto the left hand side. So we'll end up with t squared on the top. And if we divide by r squared down over to the left hand side, we'd end up with t squared on r cubed. So there's the relationship that we're looking for from Kepler's third law. And if we move everything else across to the right hand side, we end up with 4 pi squared on gm. So that value of k that we were referring to earlier is actually related to those quantities, 4 pi squared over gm, where m is the mass of the Sun in this particular case. So we've got now an equation that represents the constant term that is given by Kepler's third law. And to make sense of that, let's have a look at this from two perspectives. So the first perspective is that we're going to consider the mass of the Sun. And the mass of the Sun is quite large. It's 1.989 by 10 to the 30 kilograms. So if we look at the value there, so if we consider t squared on r cubed, that's equal to 4 pi squared on gm. So if we substitute in what we know there on the right hand side, so 4 pi squared over 6.67 by 10 to the negative 11, that's the universal gravitational constant, multiplied by the mass of the Sun, 1.989 by 10 to the 30, the value that we get out from that calculation is 2.98 by 10 to the negative 19. Now the units here we can figure out if we go all the way back to what t squared on r cubed would be. T would be measured in seconds, so t squared would then give us seconds squared. The distance r would be measured in meters, so r cubed means that we've got per meter cubed. So there's the value of t squared on r cubed if we consider the mass of the Sun. Now if we consider Earth, so this is now looking at one of the planets that orbits the Sun. If we consider Earth, the sidereal period is 365.256 days, and that corresponds to a time of 3.15581 by 10 to the 7 seconds. And the radius, or the average radius of Earth's distance from the Sun is 149.6 by 10 to the 6 kilometers, or 149.6 million kilometers. If we convert that to SI units, that's 149.6 by 10 to the 9. So kilo being by 10 to the 3, so 10 to the 6 by 10 to the 3 gives us 10 to the 9, 10 to the 9 meters. And if we look at the value of t squared on r cubed for Earth, that's a value of 3.15581 by 10 to the 7, that's all squared, divided by 149.6 by 10 to the 9, and that's cubed, and the answer that we get from that is 2.975 by 10 to the negative 19, and again same units as before, seconds squared per cubic metre. So you can see there those two values, 2.98 by 10 to the negative 19 and 2.975 by 10 to the negative 19, fairly close. So it's, we can see there that Kepler's law does seem to hold when we consider those two different perspectives, the mass of the Sun and then the orbital data for the Earth. We'll have a look at other planets and see how close they are to that value, and then we'll go from there in class and have a look at those calculations. One last thing to note here then is that when we consider Kepler's laws, they were formulated based on our solar system. So when we're considering our solar system, it's there are a lot of other solar systems that we've seen out there that are fairly similar to our solar system, but it's important to note that these laws are based on our solar system. They would also apply to anything that sort of resembles our solar system. And by that what I mean is they apply to other orbital systems where you have a fairly large mass in the middle. So where there is a large central body. And by large central body we basically mean that the majority of the mass of the solar system is going to be concentrated in that central body, or the mass of the orbital system I should say here. So like I say, there's a lot of other solar systems out there that we've observed that seem to resemble that sort of orbital system, but there's one within our own solar system that we can, or a couple, one in particular I'm going to mention here, being the moons around Jupiter. So the mass of Jupiter compared to the mass of the moons that orbit Jupiter means that we can also treat that situation as where Kepler's laws could apply. Obviously it's going to be a little bit different considering the mass of Jupiter is much less than the Sun, so that constant for Kepler's third law would change if we're looking at the orbital system with Jupiter at the centre. However, it doesn't apply to all orbital systems. And a great example of where Kepler's laws don't work would be a system where you don't have that large central mass, and that would be something like a binary star. So where you've got two stars that are orbiting each other, then these laws, Kepler's first, second and third law, don't apply quite as simply. You can extend it a little bit further, make them a little bit more involved, but like I say, that's a bit outside the scope of this particular course. All you need to worry about is how Kepler's laws of motion apply to our solar system. Again, we'll have a look at a few problems in class. We'll look at the data for other planets. We'll look at moons around Jupiter, just to make sense of how to use this particular equation.